Cycle 1, Lesson 6, investigating properties of sinusoidal functions. So we've looked at a periodic function in the last lesson, and a sinusoidal function is just a specific type of periodic function. It comes from graphing an angle, or it doesn't have to be an angle, but it starts from trigonometry, sin as in sine, okay? And it starts from graphing an angle to the value of the sine of that angle, or the cos of that angle. And the angle would be on the x-axis, the sine or cos or tan or whatever of that angle would be on the y-axis. And it can be extended to things that aren't involving trig ratios, but that's what we're going to use as our model. Okay, so just to see what it says here, a sinusoidal function is a periodic function, right? Periodic, whose graph looks like a smooth symmetrical wave where any portion of the wave can be horizontally translated into another portion of the curve. That's just true of any periodic function. We can horizontally shift them left or right to another, by one cycle to another portion. And graphs of sinusoidal functions can be created by transforming the graph of y equals sine x. Again, what I was just talking about, y equals cos x. And those are going to be our two basic models. So this lesson is just about an introduction to them, and we'll get more in depth with them in later lessons. So example 1, state whether the following are periodic or not. If they are periodic, are they sinusoidal? So this one, if I'm going to consider these A, B, and C, and so on, this is periodic. It definitely looks like it's going to repeat, and it does look sinusoidal. Some people say sinusoidal, some people say sinusoidal. I don't care. It's up to you. I think I tend to go with sinusoidal. So it's periodic and it's sinusoidal. This is not periodic, is it? For B part. Periodic. Not periodic. It doesn't look like it's repeating. It's just going upwards forever. How could it repeat if it doesn't ever come down and go up? It has to have some sort of repeating action to it, like C part. That one repeats. It's not sinusoidal. It is periodic because it does definitely look like it's repeating, right? If I was to start here and follow the graph, then once I get back to about here, then it's starting over. So that's what makes it periodic. And I guess I could have done that for this one as well. This one starts, goes up, comes back down, and once it gets there, then it's repeating again. Anyway, so we got periodic for C part, but it's not sinusoidal. The reason it's not sinusoidal is because all sinusoidal graphs, sinusoidal, there we go. The reason it's not sinusoidal is because all sinusoidal graphs have this wave shape. So in that case, we can say that this one is not sinusoidal either. Waves don't have these points on the tops and bottoms of them. Yes, it's periodic, but again, it's not sinusoidal. So, as I mentioned, sinusoidal graphs are related to trigonometry. So we're going to have to talk a bit about trigonometry in order to talk about sinusoidal graphs. So, just scanning ahead to remind myself of what's coming up. Oh yes, lots of stuff to talk about, right? Again, this is just an overview, an introduction to sinusoidal graphs. We're going to get more in depth with them later. So I'm going to go fast like I normally do in my lessons, but again, you can always pause, go back. But I'm also not going to get in depth with any one thing since we're going to be hitting this stuff again in later lessons. Introduction, keep that in mind. So determine the coordinates of the new point after a rotation of 70 degrees about 0, 0 from the point 3, 0. So for sinusoidal graphs, we're thinking about angles on a Cartesian plane. That's the basic idea. So you can see we got this XY Cartesian plane. And for angles on the Cartesian plane, we always start at the positive x-axis. So this is what's called the initial arm. And we generally, unless we're told otherwise, go in a counterclockwise direction. And so 70 degrees is going to take you over to, well, where you can see this arm here. And it says, find the coordinates of the new point after a rotation of 70 degrees. So what do we know? I'm going to erase this because it's cluttering things up a bit. But if it's got the point 30, we know the radius of the circle is 3 units, right? So even if we move over to here, to this point that we want to find the coordinates of, this arm here has still got to be 3 units, right? So this is 3 units because this is 3 units, and all we've done is rotate it. Radius is radius no matter what. But I'm not going to worry about the one on the x-axis. I'm just going to draw a new triangle. It's going to have a hypotenuse of 3, and it's going to have an x length and a y length. Well, if I can figure out what that x length is, that's going to give me my x coordinate. If I can figure out what that y length is, it's going to give me the y coordinate. So let's start with x. If I wanted to find out, let's start with sine, okay? Because we usually start with sine. So we know that sine theta, if theta is just an angle, is equal to opposite over hypotenuse. If I fill in some specifics that I know for this triangle, I know that theta is 70 degrees. I've been given that. The opposite side is represented by y, and the hypotenuse is the 3. So if I rearrange that, if I multiply both sides by 3, I'd get 3 times sine 70 equals y. And then I can find out what 3 times sine 70 is to get my length for y. And I'll do that right now. So 3 times sine 70, and it tells me it's 2.82. Let's go to 2 decimal places. So y equals 2.82. So that's my answer for the y coordinate. If I want to find out the x coordinate, I can use cosine, because cos uses adjacent over hypotenuse. And so if I went cos 70, that would equal the adjacent side is x over 3. So same thing, it's going to be 3 times cos 70 is equal to x. And if I type that into the calculator, then I'd have 3 times cos 70, and that's 1.03 to 2 decimal places. X equals 1.03. So the ordered pair, I guess I could probably round a bit more. So the ordered pair, xy, is going to be 1.0 and 2.8, respectively. So the 1.0 just came from getting my x coordinate there. The 2.8 came from getting my y coordinate, like that. And that is my overall answer. So that's a specific one, but you can probably imagine how we could extend this to find any point on that circle by using sine to find the y value and cos to find the x value. So anytime I want to find cos, so the x value first is always going to be the radius times, because the radius in this example was 3, the radius times the cos of the angle. So pxy for the radius on a circle with the radius of r is going to be r cos theta. Theta again is the angle, r is the radius, and the y coordinate would be r sine theta. So this is a formula that we can now use to find any point, as long as we know the radius and the angle that we're looking for. What else do we, again, we're just sort of doing a sampling of different trig things that are going to help us out later. So again, sort of going to be all over the place a little bit in this lesson. Going back to function notation, what if f at x equals sine 3x? So this is just to show us how we can use function notation even when we're dealing with trig values. So if f at x equals sine 3x, and I want to find f at 25, let's do that in blue, f at 25 degrees is going to equal sine of 3 times 25 degrees. So just like in other functions, I'm going to substitute in whatever x is equal to and work it out. And I'm going to follow order of operations. 3 times 25 is 75 degrees. So I'd find whatever the sine of 75 degrees is. And it turns out to be 0.97 if I round it, 0.97. Maybe, usually I go for, I guess, for more decimal places when I'm doing a trig ratio. Let's say 0.960. I'll go to 4. That's sort of a 0.9660, 2 sixes. All right, so we can plug numbers in just like we can for any other kind of function. If f at x equals cos x and f at x equals 0, calculate x for 0 to 360 degrees. So again, here's our function. We're being asked to plug this in, but again, this time they're not notice this is different. They're not telling me that x is 25 degrees or that x is 0. They're telling me that f at x equals 0. So I need to plug this 0 in for the y coordinate. So I would put 0 in for f at x, and I'd have 0 equals cos x. And I'm just to find that for between 0 and 360 degrees. Well, I know that if I want to solve for the angle, and really it's asking me to find the angle, then I can do the inverse cos of each side. So that's just doing the cos -1. So cos -1 of 0 is going to equal x. In other words, I'm bringing that cos to the other side, it becomes a cos -1. So that's all well and good. So I'll do cos -1, 0, and it equals 90 degrees. So x equals 90 degrees. But that's not my only answer. There's actually going to be another value that gives me a cos x equal to 0. And to understand that, I should just draw a quick sketch on the Cartesian plane. So we know that 90 degrees, from my initial arm, if I start on my initial arm, then 90 degrees is going to take me straight up to here. Right? So there's 90. And I can't really draw a triangle out of this, can I? Because it's really just a straight line, a straight vertical line. If I try to, imagine I draw a triangle and, I could draw a triangle like this, or I could draw one that's a bit taller like this. And I could keep making them taller, and you can see how the x value is getting smaller and smaller. X is this side here, isn't it? If I keep making that x smaller and smaller, eventually I'm just going to get a straight line up and down. If I have this vertical line, but I think about it like a triangle, let's think about opposite, adjacent, and hypotenuse. Assuming the angle's here. So the angle is 0. Sorry, the angle is 90. It's a straight up and down line. Well, if we think of this like it's a unit circle, in other words, if the radius is 1, then the radius, the hypotenuse, is going to equal 1. The adjacent, which is the x value, is going to equal 0. There's no horizontal anything there. And the opposite is going to equal 1 as well. The opposite and the hypotenuse are going to be the same. And the reason, if we think about it that way, then we know that cos equals adjacent over hypotenuse, doesn't it? So it would be 0 over 1. That's, without going to the calculator, then I could get cos theta, or cos 0, is equal to adjacent over hypotenuse, 0 over 1 equals 0. Again, what I was looking for. Why am I telling you this? Look back at the Cartesian plane. Is there any other angle between 0 and 360 degrees, which, 0 to 360 degrees is one full circle, where I'm going to have an adjacent side of 0? So let's do this in light blue. If I start here, I've already got the 90 degrees. If I keep going Remember, I'm thinking if I have a radius of 1. Well, nothing here, nothing here, nothing here. Oh, wait a second. Here's a vertical line again, right? If I get back to a vertical line so that I'm starting on the x-axis, going around until I get to here, I'm back to having a vertical line. My adjacent side is going to be 0 again. What's the angle that goes with that? Well, that's 270 degrees. So there's 2 answers, it turns out, and there's often going to be 2 answers we're going to see for between 0 and 360 for a full rotation on the Cartesian plane. That's going to give us an answer for questions like this. And again, we're going to spend a lot more time on this kind of thing as well. So that's just sort of a taste to get us thinking about how things work when we put them on a full Cartesian plane with a full 360-degree rotation. Sketch the sinusoidal graph with a period of 10, an amplitude of 2, an equation of the axis of 1, and a number of cycles 3. Okay, so I've told you in a previous lesson what order you should be doing these different things in. So we got this value, period 10, amplitude 2, equation of the axis 1, and number of cycles 3. You may remember me saying that I would always start with the equation of the axis. So if the equation of the axis is at 1, I'm just going to draw a little horizontal. I like to use a dotted line just to represent that it's not really there. It's just sort of something I'm using as a guide, but I'm putting that at 1. So I start with that as my first step. The period is 10. Well, so what would I do next? Let's see. I might do look at the amplitude next. So the amplitude is 2. So from that dotted line, I'm going to go up 2, so I'm going to have a maximum value at 3, and I'm going to go down 2 from that dotted line. I'm going to have a minimum value at -1. Remember, amplitude is the distance between the axis and the max or the min. So that's, my whole graph's got to go no higher than +3 and no lower than -1. Next, I'm going to look at the period, which is 10 units. And so I know that I have to get a full cycle in by the time I get here to 10. So things are starting to come together. So let's say I want to start, without any other instructions, I might start on the axis of the curve. So I'll start here at 0, 1. If I have to get a full cycle in 10 units, then I'm going to end on the axis of the curve at 0, 10. Sorry, at 10, 0. Sorry, one more time, at 10, 1. Being periodic, it's going to have this wave shape that we saw up here. It's very symmetrical. That means it's going to exactly halfway along, at 5, it's going to be back at the axis of the curve. And exactly halfway between 5 and 0, it's going to hit its maximum. So that would be at 2.5. So I can put a point up here, and exactly halfway between 5 and 10, it's going to hit its minimum. That's at 7.5. So if I connect these dots up into a smooth curve, then that's one cycle. Then the last part I look at is the number of cycles, and I repeat it. So I'm going to have another cycle by the time I'm at 20, a third cycle by the time I get at 30. Those are going to be divided in half for the where it crosses the axis again. So we'll have things at 12.5 and 17.5 and 22.5 and 27.5 for the max and min and all that. And there is my 3 cycles, period 10, amplitude 2, axis of the curve at 1. So you always want to think about things in that order. Complete the following using your calculator to determine the y values. So let's just do this quickly. So you make sure your calculator is set to degrees. And I'm going to do it on a different calculator so I can just go a bit quicker and not have to switch back and forth. But if I type, if I'm given angles here, think of that as my x value, and sine of theta as my y value. If x equals 0, then if I take the sine of 0 on my calculator, sine 0 equals 0, it tells me, okay? If I take x equals 30, just take an angle of 30 and do sine of 30, sine 30 on my calculator is 0.5. And so I'm just going to keep typing these different values in. Sine 45 is 0. I'm just going to round to 2 decimal places, 0.71. Sine 60 is 0.87. Sine 90 is 1. Sine 120 is 0.87 again, it turns out. Interesting. Sine 135 is 0.71 again. So I'm starting to see some repetition. 150, sine 150 is 0.5. Sine 180 is 0. So my values went up to 1 and they came back down. If I carry on in the next row, I'm just going to just keep going. So 210 degrees, an angle of 210 degrees. When I take the sine of that, is going to be negative 0.5. And then sine of 225 is negative 0.71. And then I get negative 0.87. And then sine of 270 is negative 1. And sine of 300 is negative 0.87, negative 0.71, negative 0.5, and back to 0 at 360. So if you're having trouble picturing these angles, go back and visualize a circle again on the plane. Remember, we can go anywhere, a full rotation, always starting at the initial arm is going to be 360 degrees. So just a quick sketch to help you visualize that. We're always starting here at the initial arm, and up to here is 90, 180, 270, 360 takes me back to where I started on the initial arm, right? So that's what we mean by an angle of 360 degrees, basically just going around a full circle to where I started. If I plot these ordered pairs, again, x is my angle, theta. Instead of calling it x and y, I'm going to call it theta. But theta is on my x-axis, and y is my sine theta, the sine of the angle. I'm going to put that on my y-axis. And I'm just going to plot these as ordered pairs. So I'm going to have this ordered pair 0, 0. I'm not going to worry about putting the degree symbol on there, but I got this point 0, 0, which is at the origin. And then I've got this point 30 and 0.5, which is here. This scale looks a little funny. I think it cut something off here. That's not 0, that's 0. It's supposed to be 0.5, and that's supposed to be negative 0.5. So it's going from negative 1 up to positive 1 for what we can see here. So then we had 0.71 at 45 degrees. That would be about here. And 0.87 at 60 degrees. Sorry. That would be about here. At 90 degrees, it was 1. Then it started coming back down again. Until at 180, I hit 0. Well, look at that. It makes a nice smooth curve that fits what we've described as a part of a sinusoidal function. And if I keep going with the negative ones, I'm going to be down here at negative 0.5 and then negative 0.71, maybe about here, negative 240, negative 1, and then again it starts going back up again, right about here, here, and here. And here's the rest of my points. Well, lo and behold, we've got ourselves one cycle of a sinusoidal function. Now the domain depends on are we thinking it goes on forever, or are we just talking about this 0 to 360? It's definitely all real numbers. As far as this graph goes, if I don't have arrows on the end, it's going to go from 0 to 360. But if we do have arrows on the end, hopefully you can see it's going to go on forever in both directions. As far as the range goes, it's all real numbers again, but you can see the lowest it could possibly go is negative 1, and the highest it could possibly go is positive 1. So it's going to go from negative 1 to positive 1. The amplitude is the distance from the axis. Well, where is the axis of the curve? The axis of the curve is the x-axis, isn't it? I'll just sketch that in lightly with a dotted line. So I'm going to jump to that one. The equation of the axis is y equals 0, the x-axis. The amplitude is the distance between the axis of the curve and the max or the min, which is 1. The period, as you can see, one full cycle takes 360 degrees. The x-intercepts, I'll highlight them. They're at 0, 180, and 360. The maximum occurs at 90 degrees. The minimum occurs at 270 degrees. Here's the max and the min respectively. in green. So that is how we can form a periodic function using trigonometry. Now we're asked to repeat this using cosine. So we're going to do the exact same thing, except that instead of typing in sine of all these different angles, I'm going to type cosine in. So you've got the idea. Let's just do it quickly now. I won't talk about it so much so I can get it filled in faster, but I'll talk a little bit, I guess, but hopefully you got the idea. When I do cos of 0, I get 1. When I do cos of 30, I get 0.87. When I do cos of 45, I get 0.71. When I do cos of 60, I get 0.5. When I do cos of 90, I get 0. We already saw that up above, right? When we did cos x equals 0, we had to solve it. We found out that 90 was the angle that gave us a cos x of 0. So that fits with what we saw before. Then it starts going down, actually. Cos 120, so when I say it starts going down, I mean it starts going into negatives, gives me negative 0.5. Interesting. And then I got negative 0.71 and negative 0.87 and negative 1 at 180. Interesting. And when I do 210, I get negative 0.87, and 225 is negative 0.71, negative 0.5, so it's coming back upwards. At 270, I hit 0 again. Remember from that previous question? Yeah, 270 did give me a cos of 0. 300, now I'm popping back up above the x-axis and getting these values, which you've already seen, and I end up at 1 again. So in order to visualize it, again, let's graph theta on the x-axis and cos theta on the y-axis. And again, doing ordered pairs, this time I'm starting at 0, 1. I'm going to fix my scale again so that it says 0.5. So I've got 0.5 and negative 0.5, so it makes sense. I'm starting at 0, 1 this time. And then I go to 0.87, and then I go to 0.71 and 0.5 and 0, and then down to negative 0.5, negative 0.71, negative 0.87, negative 1. Then I start going back up again, and it's all very symmetrical, isn't it? You can see the points as I fill them in. They're really forming that wave shape. And it's just very much like the wave shape that we did for sine. And if I connect the dots, hopefully you'll really be able to see it clearly. I would say that it's identical to the wave that we saw for sine, with one difference. It's like it's been shifted a little bit to the right. No, if we took the sine graph and shifted it to the left, we'd get the cosine one. Otherwise, they're identical. They have the same max min, they have the same axis of the curve, they have the same period, everything's the same. So again, that means that the domain is all real numbers, and if we're stopping between 0 and 360, then that would be our limitations in this case. The range, just like for the sine graph, was from -1 to +1. The axis, the equation of the axis, once again, you can see that horizontal equation or axis is on the x-axis, so the equation would be y equals 0. The amplitude, once again, from the distance between the axis and the max or the min, is still 1. Remember, we don't put a -1, even if I'm measuring downward. I just want to know the distance. I don't care if it's measuring up or down. So the amplitude's still just 1. The period's 360 degrees, right? It starts at 0, it does and goes to 360. Then it would start over. If I was to keep going on this graph, it would go like this. But that's not what we're asked to do, so I'll stop that. X-intercepts are different on this, though, from the sine one, because it's been shifted. There's only 2 x-intercepts, and those are at 90 degrees and 270 degrees. The max occurs at 1, the max is 1, it occurs at 0, but it also occurs at 360. So it occurs at 0 and 360. And finally, the minimum occurs here at 180 degrees. So that's a whole lot of stuff to digest. And it's just an overview of some of the things that we need to know to work with trig, with sinusoidal functions. So all you need to do now is just make sure that you answer these questions, understand them well, ask me if you have any problems. And then as we do future lessons, we're going to start to fill in some more of the gaps, and the puzzle will hopefully all come together. But you have to put that effort in at this point to get the basics down.